Now you might be wondering, are nucleophiles and bases the same thing? They look very similar. Let's talk about it. So, yes, nucleophiles and bases are very similar. They often have a lone pair they even often have negative charges. They always have a pi bond that is ready to go and attack. But they differ in one thing. They differ in what they are looking for, what they are attacking. So bases always attack protons and nucleophiles always attack electrons. So let's say that one more time. So remember that bases, they always have a lone pair, just like that. Sometimes they have a negative charge, sometimes they don't. They are always looking for acids, right, to go and attack and get that proton. Nucleophiles, remember we've said this many, many times, they are looking for electrophiles to go and attack them. So that's one of the main differences, what they are looking for and what they attack. So they are very interrelated and often they go side by side. But let's talk about what basicity and nucleophilicity are. So basicity comes from base, and if a base is a molecule that wants to go and get protons, the basicity is a measure of how ready is that molecule to go and get that pair, that proton, sorry, to go and share that electron pair with a proton. In the same way, if a nucleophile goes and attacks an electrophile, right? The nucleophilicity is a measurement of how ready is that nucleophile to go and attack. So what I can tell you about nucleophiles is when a nucleophile is a strong nucleophile, the reaction will happen fast. And when the nucleophile is weak, the reaction will be slow. Right? So you see, it's characterized by a rate constant. So it has to do with time, with how fast it goes. It's related to kinetics. So that's why we talk about fast and slow. So let's talk about the cases where nucleophilicity and basicity go side by side, meaning that they follow the same trends. Okay, so the first example is when you have two nucleophiles that have the same nucleophilic atom. That is, imagine we have OH minus versus you've done the acid and base chapter, you can figure out which one of these ones is a stronger base. Pause the video here and try to remember. You probably saw it here, but let me just remind you of why the OH minus is a stronger base than the acetate here. So the OH minus has 3 pairs of electrons, and the oxygen also has those 3 pairs. So they share the same thing. But the difference is that in the OH minus, the electrons are only localized in that oxygen, whereas here, the electrons can move around. They can delocalize and go up and down. So that negative charge, it's delocalized. That is making these a weaker base. And if it's a weaker base, it's not ready to go and attack. So this is my stronger base. And at the same time, a stronger base, it's also a stronger nucleophile. So they go together. In this case, strong base and strong nucleophile are the same. And in this case, of this pair is this one right here. So of these two, this is the stronger base and the strong nucleophile. So here we have another example. We've talked about it before, but so we can have OH minus that has the 3 lone pairs, or we can have a molecule that is not charged. So if we talk about which one of these two is more ready to go and attack, remember that a species that is negatively charged or that has it can be negatively charged or positively charged is more ready to go and attack because is more unstable. So because this O minus is more unstable than the water that is pretty stable, this will be a stronger base. So because this will be the stronger base, it will also be a stronger nucleophile. So a negatively charged species is stronger than a species that is neutral like this as a nucleophile, because the electrons are more ready to go and attack than they are right here. Right here, they are stable. In the water, those electrons are fine. They have no necessity to go and attack. However, here, this oxygen is not at a stable position because it has that negative charge right there. So it's very, very ready to go and attack. Remember, if we were to draw an energy diagram, the water will be here and the OH minus will be here. So because this one has a higher energy, it's ready to go and attack. This one is not so much. So in this case, basicity and nucleophilicity go together. And here, same thing, because we increase the basicity as we go towards the left in the periodic table, it will also increase the nucleophilicity. And remember why is that? Because the negative charge on the carbon is at a much worse position than it is in the fluorine. Fluorine is more electronegative, so it's happy to have that negative charge. However, carbon is not so electronegative, so it's not happy to have that negative charge. So if we were to draw an energy diagram here, the carbon will be here, then the nitrogen, then the oxygen, and then the fluorine. So the one that has the highest energy is the one that is ready to go and attack. So it's the most basic. And in this case, basicity and nucleophilicity go side by side. So here you have some of the most common nucleophiles, and you're going to see this very often. So remember that these ones that have negatively charged, these are the most these are the stronger nucleophiles, and these ones right here that are neutral, these are not so ready to go and attack, but they can still act as nucleophiles. So these ones are strong, and these ones are weak nucleophiles because of the charge, right? These are neutrals, these have a negative charge. The code for today's class is 3756. However, nucleophilicity does not always go together with basicity. Let's see a couple of examples. The first one is when the molecule has a steric hindrance. When that happens, you imagine that you have one ethoxide right here and this terbutoxide. Both of them have negative charges and they are electron rich, which it means that potentially they could be good nucleophiles. However, this molecule right here, the terbutoxide, has a lot of steric hindrance. And when that happens is that there will be a decrease in the reactivity of this molecule as a nucleophile. Let me try to explain you why. So imagine you have these right here, and the terbutoxide on the other side is trying to react with, let's say you have that alkyl bromide. So what will happen is that your nucleophile will come and attack, kicking the Br out. And the same will happen here with your terbutoxide. However, because this molecule at this point has become so big, it is difficult for it to reach that electrophile. And so because of that, this molecule will become a worse nucleophile than this one right here. So this one is a better nucleophile This one is a worse nucleophile because of that steric hindrance that doesn't allow it to reach the electrophile, right? However, in terms of basicity, let's look at these two molecules. Both of them have a negative charge on the oxygen, so if we go by Ario, they are very similar. However, think about this. Do you remember what alkyl groups can do in terms of electronics? Alkyl groups, I don't know if you can remember, we saw these in the acid-base chapter. They do the opposite of what a fluorine or a chlorine could do during the inductance. So do you remember that when we have a negative charge, right? Just like this one, but we have a fluorine. What will happen is that the fluorine will pull electron density away from the negative charge, and so that will lower the energy of the overall molecule because the negative charge will be distributed all over these all over here, and so that will lower the energy of these molecule. However, when we have alkyl groups, the opposite things happen. So an alkyl group, remember we have CH3, 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 that will donate electron density towards your molecule. So think about this. You are donating electron density to a molecule that is already negative. So you have electrons going in this direction. What that is doing is destabilizing this base. And if you destabilize the base, the energy goes up. And if the energy goes up, then it becomes a better base. So in this particular example, the ethoxide right here is a better nucleophile because it's smaller and it can reach my electrophile. However, my terbutoxide is a better base because of these alkyl groups that are electron donating. Another example of when nucleophilicity and basicity don't go together is when there is polarization. So let's talk about polarization. Imagine that we have a molecule, Br minus. This molecule is going to be really big. So the Br is going to have enough space for the electrons to be all over here, and so they can move around. What happens is that if an an external field is applied to the BR can shift. And so that's what we say when we talk about polarizability, is that a molecule or the electron density of a molecule can be modified. And so what that will do to us is that BR, or the electron density around the BR, it can be moved and it can go and attack somewhere else. So that makes it a better nucleophile. So when a molecule is polarizable, such as Br, what it means is that it will make it a better nucleophile. Because the electron density can be displaced, imagine all these electrons going in one direction and one direction only to go and attack. So that is the exact definition of a nucleophile. It's a molecule that will go looking for an electron. That's the definition of a nucleophile, a molecule that will be looking for an electrophile. So if we look at these again, let's talk about it in terms of base and nucleophile. So as I said, because the molecule is large and it can be polarized, then that means that this will be a good nucleophile. So this will be good. However, let's talk about the base. This base comes from HBr. So try to think back and think about the acids and base chapter and try to think if HBr was a good or a bad acid. HBr is a good acid because if that H is taken away, then what you get is this Br, and the Br is large, so it can stabilize that negative charge well. So then that will make this base a weak